Hello everyone. Today we are going to discuss today's JEE Mains Model 4 examination, which is based on chemical kinetics and isomerism. In isomerism, we have structural isomerism and geometrical isomerism. Okay. So first, what they have asked in 26th one, which of the following compounds is isomeric with propanoic acid? So what is the propanoic acid formula? CH3 bond, CH2 bond, COOH. How many carbon atoms? C3. How many hydrogen atoms? H6 and O2. It is CN, H2N, O2 is propanoic acid. The same number of carbons, hydrogens and oxygens should be there in the isomeric structure. Now if you check this one, here also how many hydrogens, how many carbons, check it, C3, H6, O2. So it is having what? Aldehyde group and alcohol group, right? It is isomeric with propanoic acid. Next, which pair of the following is not an example of position isomerism? Here N-pentane and isopentane. These two are examples of what? Chain isomers. They are chain isomers but not position isomers. These are chain isomers. Okay. Next, number of structural isomers of 3-degree amines possible with the molecular formula C6H15N. Okay, so they have asked about 3-degree amines. What do you mean by 3-degree amine? The nitrogen which is attached to 3 carbons. This is 3-degree amine. So if it is taken like this, it is 3-degree amine we say here. Nitrogen should be attached to 3 carbon atoms directly, which is called 3-degree amine. So the possible structures with this molecular formula we have to draw. So for drawing the molecular structures, different possible structures, we use one concept called DBE, double bond equivalent. So by calculating double bond equivalent of the given structure, we can understand how many double bonds, how many triple bonds, how many rings present in the given structure. So with the DBE value, we have to draw possible structures. So here in this case, we get 7 types of structural isomers. Okay. Next one, the following are metamers of ethyl acetate, except the following 3 are metamers of ethyl acetate, but only one will not be. That one we have to identify. Ethyl acetate formula, tell me first. Ethyl acetate. So acetate means CH3 bond COO. Okay, bond. Here acetate means what now here? CH3COO, and ethyl group is what now here? C2H5. So it is ethyl acetate. So in this here, ester group, if we take on both the side of ester group here, COOR, it is, or it is COOR. So here on either side of COOR group, methyl group and ethyl group are there here. Methyl group and ethyl group. So this type of compounds with 2 different alkyl groups on both the sides of divalent functional group are called metamers. And here if you take this one, methyl acetate. What is the formula of methyl acetate? CH3 bond COO is acetate. Methyl is CH3. Now see here, on either side of acetate, a COO minus CH3 and CH3 there. And in this case now here, how many carbon atoms? 3 only. But here in this given structure, 1, 2, 3, 4 carbons there here. So it cannot be metamer. It cannot be isomer with given ethyl acetate. Is that clear? Next, the type of isomerism. Okay, which is shown in the given compound they asked here. So the type of isomerism shown by nitromethane. So nitromethane is given by CH3 bond NO2. This nitromethane, NO2 group and CH3. So in this case, the nitro group is attached to this carbon directly. So it is alpha carbon. What is alpha carbon? Alpha carbon has what now? Alpha hydrogen atoms. 3 alpha hydrogen atoms present here. So one alpha hydrogen may be transferred to the more electronegative oxygen. So atom 1, atom 2, atom 3. From atom 1 to atom 3, 1,3 shift will take place. So hydrogen may be shifted to oxygen from carbon. From one polyvalent atom, the hydrogen transfers to the other polyvalent atom. Here, what is condition for exhibiting tautomerism? More electronegative atom should be having multiple bonds. Okay, more electronegative atom should be attached to the given atom with multiple bond, and there should be alpha hydrogen, at least one. Here, 3 alpha hydrogen atoms are there, and more electronegative oxygen is having multiple bond, double bond. So it will exhibit what now? Tautomerism. Next, tautomerism is not exhibited by. Conditions I told you just now. Tautomerism to exhibit, there should be labile hydrogen. So here, this point is what now? Your alpha position. Here it is CO. CO is what? Ketone group here. To this CO this is attached. It is alpha carbon. Okay. Here alpha hydrogen is there, but this alpha hydrogen is not labile. It is not labile. That means what now? Here this alpha hydrogen cannot be transferred from alpha carbon to oxygen. This hydrogen is not transferable. The hydrogen which is directly attached to the double bonded carbon, sp2 carbon, cannot be transferred. So this compound has, again, this side also same thing again. Here also hydrogen is there, alpha hydrogen is there, but it is attached to what? sp2 carbon, double bonded carbon. So it also cannot be transferred to oxygen. This is also same thing. For this CO group, it is alpha. Again, what? No labile hydrogen here. Alpha hydrogen is there, but that cannot be transferred to oxygen here. So this compound cannot show tautomerism because of absence of what? Labile hydrogen atoms. Next, which can show geometrical isomerism. Okay, to show geometrical isomerism condition what? There should be multiple bond, double bond between carbon atoms. On each double bonded carbon, 2 different groups must be attached. On this double bonded carbon also 2 different groups are present, right? And here the 2 hydrogen atoms are below the plane of the double bond, and these 2 methyl groups are above the plane of the double bond. So here in this case, what we have to understand, similar groups on the same side of plane of the molecule. So it is cis isomer. It is cis geometrical isomer. It can also have what now? Trans geometrical isomer. So it can exhibit what? Geometrical isomerism. If similar groups are present on the double bonded carbon, that cannot show what? Here 2 similar groups on double bonded carbon. Here 2 similar groups on double bonded carbon. So if similar groups on same double bonded carbon, that molecule cannot show geometrical isomerism. Only the C can show geometrical isomerism. Next, the correct structure of trans 2-hexenol. Here al is what now? Secondary suffix. Aldehyde. Bond CHO should be there here. Hex indicates root word which contains 6 carbon atoms. Okay. So here ene means double bond at which position? Second position. 2-ene. So now here it is first carbon atom, it is second carbon atom, third, fourth, fifth, and sixth carbon atom here. So after second carbon, what is there here? Double bond is there. So it is what now? 2-ene. So trans 2-hexenol. See now in this case, double bond is there now between 2 and 3 carbon atoms. Double bond is there. So now this double bond contains hydrogen here. Okay, and the other group is there here. On this double bonded carbon 3, 1 hydrogen is there. This group totally belongs to 1 group here. And on this double bonded carbon, 1 hydrogen is there, and CHO is there. On this double bonded carbon, 2 different groups are there. On this double bonded carbon also 2 different groups are there. Now check it here. Hydrogen is above the plane, hydrogen is below the plane. Similar groups on opposite sides now here. So it is what now? Trans isomer. Okay. Next one. Among the following compounds, the one which does not show geometrical isomerism, Check it here. It is imine. Double bond NH is called what now? Imine. So here C double bond N type of compound it is. C double bond N, C double bond C will be showing what now? Geometrical isomerism. Now what is the condition for this type of ketimine? Here ketone it is. C double bond O is replaced by double bond NCH3. Here double bond NH replaced what? Double bond C. Double bond O. So C double bond O ketone, the double bond O is replaced by double bond CH3, double bond NCH3. So in this case, what we have to understand is that in this ketimine, what is called ketimine? In this ketimine, on the double bonded carbon, two groups should not be same. If two groups present on the double bonded carbon are same, that will not show geometrical isomerism. Geometrical isomerism. Syn and anti cannot be shown here. Syn anti isomerism cannot be shown by this type of compounds in which the double bonded carbon contains two similar groups. So it cannot show geometrical isomerism. Next, the number of cis trans isomers possible for the following compound. Okay, so in this case, now check it here. So this carbon, if you check, double bonded carbon, right? So here one hydrogen is there, here one hydrogen is there, right? So when two hydrogen atoms are present on opposite side, it is trans. For the same structure, we can also have what? Cis, right? So and one more thing here, if you take these two double bonded carbons, here one hydrogen is there, here one hydrogen is there. Okay, this hydrogen can be what now here, this carbon has no hydrogens in this because here C already has 1, 2, 3, 4 bonds now. Only C is there here. Only C is there. Here, this double bonded carbon has CH. Okay, and moreover, this is what now here 5-membered ring. 5-membered rings will have a ring strain. Okay, so here CH on this double bonded carbon, two different groups are not there. Two different groups are not available here. And also what we have to understand here at this point, we have trans and cis, both we have. So at this, around this double bond, we have cis and trans isomerism. Around this double bond, there is no possibility for cis and trans isomerism. So only cis and trans, how many there totally? 2 isomers will be possible. Only cis and trans, that's all. One cis and one trans. Next one, degree of unsaturation. Degree of unsaturation. So here, one double bond is equal to 1. Okay, so one double bond, C double bond is equal to what? 1. And C triple bond, C is equal to what? 2. One ring, any ring. Any ring is equal to what? 1. So any ring is equal to 1. Not only this hexagon, any ring is equal to 1. One triple bond is equal to 2. And one double bond is equal to 1. So now check it, how many rings totally? 2 rings. The 2 rings means what? 2. Plus, how many double bonds? 1, 2. 2 double bonds. 2 double bonds means 2. Plus, how many triple bonds? 1 triple bond here, 1 triple bond here. So here, for this triple bond, the degree of unsaturation 2. For this triple bond, degree of unsaturation 2. So 2 plus 2, 4. So totally how much? 8. So 8 is the degree of unsaturation of this compound. Which of the following pairs is the chain isomer? Which pair is chain isomers in the given? Okay, now you see in this parent compound has 1, 2, 3, 4, 5, 6 carbon atoms. In this 1, 2, 3, 4, 5 carbon atoms. Here what is X value? 6. Here what is X value? 5. X value indicates what here? Number of atoms in the parent chain. In the parent chain here, 6-membered ring. There are 6 carbon atoms. In this here, in this parent ring, 5 carbons there here. So X value 5. And here what is Y value? 1. Y value 1 indicates what now? Y value 1 indicates what? Here 1 CH3 is there now. So this Y value 1 indicates what? Number of carbons in side chain. In the side chain, 1 carbon is there. Here Y is equal to 0. In this molecule, there is no side chain, right? There is no side chain. When there is no side chain, here Y value will be 0. So when X and Y values are different, we say chain isomers. So these two are chain isomers, we can say. If X values and Y values are same for two compounds, they will be taken as what? Position isomers. So this B has what now? X and Y values different. Therefore, chain isomerism is shown here. Next, molecular formula C4H8. Okay, which type of isomer will not show here? Molecular formula C4H8. Which type of isomerism will not show? Means what now here? This molecule with C4H8 formula cannot show which type of isomerism they are asking here. So it cannot show metamerism. For metamerism, what is condition mark? Bivalent group should be there. Like this bond, O bond should be there. or bond CO bond should be there, or bond COO bond should be there. Like this, if a divalent group is there on either side, different alkyl groups if present, that will show what? Metamerism. But in this case, metamerism is not shown here by this one. Okay. Next one. Minimum carbon atoms are required to ketone to show position isomerism. To show position isomerism, how many minimum carbon atoms must be there? 5 carbons. Suppose you take 1, 2, 3, 4, 5 carbon atoms. If double bond is here, it is 3 on. If double bond is here, it is 2 on. If it is double bond here, a double bond O, 2 on again. C double bond O, 2 on. Here C double bond O, 2 on. Here C double bond O. It is what now? It is 3 on. So like this, the ketone should be having what now? Ketone should be having minimum 5 carbon atoms to show position isomerism. Here it is 3 on, it will be 2 on. Okay, next. Now they have given a 6-membered ring with one double bond, 5-membered ring with one double bond. It is 1, 2, 3, 4, 5, 6, 7, 8. 8-membered ring here. So carbon atoms more than 7 here. Here carbon atoms less than 7 in the ring. Here carbon atoms less than 7. Okay. So if the number of carbon atoms is equal to or greater than 7, that molecules will show geometrical isomerism. You know, these three are what now? Cycloalkenes. Cycloalkenes. The cycloalkenes with the number of carbon atoms equal to or greater than will show what? Will show the geometrical isomerism. Because here, in this case, here suppose hydrogen is there. Here hydrogen is there. These two hydrogens cannot be written inside. Inside H cannot be written here. Okay, because around this double bond, the twisting of this bond, CH bond inside the ring cannot be taken off. Okay, so here strain will be the ring strain is there here. So if number of carbon atoms is less than 7 in cycloalkene, in that case, what happens now? Due to ring strain, the hydrogen atoms will not be rotated, means the bonds cannot be turned. The turning of CH bonds will not be possible here around this double bond. That's why here in this, how many carbon atoms are there in the cycloalkene? More than 7 there, 8 carbon atoms. That is why this only can show what now? Geometrical isomerism. Only structure 3 can show geometrical isomerism because the number of carbon atoms in the cycloalkene is greater than 7. Next, the total number of possible dichloro derivatives of isobutene. Isobutene. Here iso means what? Last but one carbon should be having what? Methyl. Out of 4 carbon atoms in the bute, out of 4 carbon atoms, 3 carbons we write in the straight chain, and last but one should be having one methyl. It is isobutene. Ene means what? Double bond. I'm giving double bond here. Suppose it is single bond. Now here how many bonds available? 3. Here one bond is available or not? No, it is not available here. The bond is not available here. Okay. Yeah. So here the bond is not available. Next here, this carbon is having what now? 3 hydrogens. This can have 2 bonds here. So it is what now here? Isobutene. Isobutene. In this isobutene here, we have to attach how many chlorine atoms here? 2. The 2 chlorine atoms can replace what? 2 hydrogen atoms. Here hydrogen, hydrogen, hydrogen. Here hydrogen, hydrogen. Like this here, the hydrogen atoms at different places we have to replace with what? Chlorine. It is isobutene structure. Okay. So in this we have to check what now here? How many dichloro derivatives are possible? Totally 5 dichloro derivatives will be possible in this case now here. By replacing what here? Here 2 hydrogens. Here 1, 1. If you replace these two, what happens now? 1, 1 dichloro will come. If you replace here, these two, 3, 3 dichloro. Because number 1 carbon will be this one. Number 1, number 2, number 3 suppose. 3 carbon atoms in the parent chain. 3 carbon atoms in the parent chain and 3, 3 dichloro, 1, 1 dichloro. After that here, this around the double bond cis and trans will be possible now. So like this, all types we have to take it. All types of isomerism means here geometrical, here in this for isobutane, total number of possible derivatives of isobutane. Okay. So by replacing different hydrogen atoms with the different chlorine atoms, we have to take what? Dichloro derivatives. Okay. So total we get what? 5 dichloro derivatives by replacing hydrogen atoms of isobutane. Okay. Next. C4H8 can have total number of dash isomers, excluding what they give here, stereoisomers. So here double bond equivalent we have to calculate. So what is the formula for double bond equivalent generally? Double bond equivalent formula what? Double bond equivalent sigma n of sigma n is what number of carbon atoms of V minus 2, valency minus 2 by 2 plus 1. So in this molecule now, in this formula here, in this formula, here how many carbon atoms? 4. How many hydrogen atoms? 8. So here, what will take number of carbons? How many here? 4. 4 into 4 minus 2. Valency of carbon how much? Valency of carbon 4. 4 minus 2, 2. 2 into 4, 8. So 8. And here, next hydrogens you take here. 8 plus hydrogens how many in this? 8. 8 into, what is valency of hydrogen? 1. 1 minus 2, minus 1. Minus 1 into 8, minus 8. Okay. So it is what now here? 0 by 2 plus 1. That equals to what now here? 1. So what is the double bond equivalent of this? 1. When double bond equivalent 1 is there, we take either ring, 1 ring may be there, or we may also have what now? 1 double bond. 1 double bond or 1 ring may be possible. 1 ring and 1 double bond. So rings how to draw now here? It is cyclobutane ring, this formula. And we can also take methyl cyclopropane. Methyl cyclopropane ring we can take. And it is the 1 double bond also may be containing, it may be containing 1 double bond also. So we can take but 1 in, but 2 in, but 1 in, but 2 in. Like that isobutene, N-butene. In that N-butene, 1 butene and 2 butene will be there. Like this, totally we get 5 isomers. Excluding what now? Cis and trans. Excluding cis and trans and any stereoisomerism, we can take only structural isomers. Okay. So ring chain isomers will be possible here, and also position isomers will be possible. Chain isomers will be possible. Okay. Next. Here, the number of amides having the formula. Okay. C4H9NO or what? So in this case also what we have to calculate first? Double bond equivalent. After calculating double bond equivalent, if double bond equivalent is 2, suppose, then we get what? 2 double bonds, otherwise 2 rings, or 1 ring and 1 double bond, or 1 triple bond. 1 triple bond is equal to double bond equivalent 2. 1 double bond is equal to double bond equivalent 1. 1 ring is also equal to double bond equivalent 1. So double bond equivalents we have to calculate first, and possible structures we have to draw. Next, which of the following compounds exhibit geometrical isomerism? Geometrical isomerism. Conditions for geometrical isomerism: there should be multiple bond. On each double bonded carbon, there should be 2 different groups. You see this double bonded carbon and this double bonded carbon. On this hydrogen 1 group, 1 atom, and CH3 1 group. On this double bonded carbon, hydrogen and CH3. So it can show geometrical isomerism. If you take this one, this is double bonded carbon, this is double bonded carbon. On this double bonded carbon, hydrogen and CH3 there, 2 different groups there. But here on this double bonded carbon, 2 hydrogen atoms there. It cannot show. It can show. Next one. In this case also, see, check it here. It is polyene. In the polyene, here H, CH3. Here on this double bonded carbon, H, CH3. So if CH3 on same side, cis. If CH3 on opposite side, trans. So on this double bonded carbon, H is there, CH3 is there. On this ending double bonded carbon also, H is there, CH3 there. On the 2 terminal double bonded carbons, 2 different groups are there now. So in polyenes, when 2 different groups are attached on the last carbon atoms, terminal carbon atoms, they will show what? geometrical isomerism. So the structure 3 also, structure 3, it is able to, or not able to, or not able to show here. Here it is having what now on both the side double bond here in this case. Okay, now check this one first. Now it is what having 3 polyene. It is polyene. Why 3 double bonds are there? Here only 2 double bonds. Okay, it is cumulodiene, means what? Cumulopolyene. Side by side double bonds are there now. Here it is polyene. Now on this double bonded carbon H and CH3 there. On this double bonded carbon also, on this double bonded carbon H and CH3. So both similar groups on same side, cis, similar groups on opposite side, trans. You have to understand. So here in this only 2 there here. Only 2 double bonds are there. Here how many double bonds? 3. Poly is this. Polyene containing 2 different groups or atoms on the terminal carbon atoms will show what? Geometrical isomerism. Okay, only 2 and 4 can show what? Geometrical isomerism. Next, type of isomerism not possible with the molecular formula C4H10O. It is what now? CnH2nO. CnH2nO. It is what now? Generally alcohol or ether type. Okay, they cannot show what now? Geometrical isomerism. Okay. Next, double bond equivalent we have taken. Double bond equivalent, if it is 0, suppose, can it have any double bond? If double bond equivalent is 0, it cannot have double bond. If it cannot have double bond, it cannot show geometrical isomerism. Okay. Yeah, this formula can show functional isomerism. Alcohol functional group may be possible, ether may be possible. And position also possible here. Methoxy possible. 1 methoxy, 2 methoxy we can take like that. The chain isomerism is possible. Only geometrical is not possible in this molecule. Next, a 46th one. A plus B gives rise to products here. One reaction is given. On doubling the concentration of A, okay, rate gets doubled. Rate of reaction gets doubled. Okay. Next, doubling the concentration of A and B, anyone, also doubles for the rate of reaction. If you double B concentration or if you double A concentration, we are getting what? The rate doubled. Okay, in this case, the rate is directly proportional to what? Concentration of A to the power of 1. And rate is also directly proportional to concentration of B to the power of 1. So in this case, what is the power of this concentration of A? 1. Okay, that's why the order of reaction will be 1 here. When the rate of reaction is directly proportional to the first power of the concentration term of the reactant, that will be first order reaction. Here, if you double the B concentration by keeping A constant, it will be double again, rate of reaction. If you keep B concentration constant and double the concentration of A, again the rate of reaction will be doubled. By doubling the concentration of A and keeping the concentration of B constant, we get the rate doubled. And by keeping concentration of A constant and doubling the concentration of B, the rate of reaction is doubled. That is given statement here. From this statement, what we have to understand, the rate is directly proportional to the first power of concentration of A. So therefore, order of reaction is what? 1. N is equal to 1. Next, the rate of equation of a gaseous reaction is given. Okay. So here A to the power of 2, B to the power of 1 is given here. Okay. If the volume of the vessel containing the reaction mixture is doubled, means reduced to 1/3. Here, thing is not there here. So initial volume we take V. Initial volume we take V. And V2, the final volume is becoming what? V by 3. That means the V is reduced to what? 1/3. The V is reduced to what? 1/3. Whenever the volume is reduced to 1/3, the molarity initially what? Concentration, molar concentration M, and final molar concentration will become what? 3M. Because molarity is inversely proportional to what? Volume. When volume is reduced to 1/3, the molarity will be tripled, 3M. So the concentration of A becomes 3A, the concentration of B also becomes 3B. Is that clear? So it is given concept here. So now what they have mentioned here in this case, check it here. So V volume is reduced to 1/3 and molarity we have to understand that it is tripled. Okay, now in this case, now R2 by R1, R2 by R1, rate of reaction final by rate of reaction initial is equal to given what in the question 9x given, 9x. Now R2 is what now, tell me? R2 is what now? Rate constant of reaction does not change. K into, okay, here 3A. The concentration of A becomes triple, na? The 3A to the power of 2. 3A to the power of what here? 2. That means what? 3 square into A square into B. B also will become what? Triple, na? The concentration of B also becomes triple. So 3B to the power of 1. So 3 power 1 into B power 1. Now this is R2. R2 by R1. R1 means what? K remains constant always. R1 and R2 cases, K will be same. And in this case now here, 1A, A square and B to the power of 1. Okay, yeah, A square get cancelled, B power 1, B power get cancelled here. So in this part now here, 3 power 1, 3 into 3 square. Okay, so here 3 square is what now here? 3 square is 9. 9 into 3. So 9 into 3. X value is what now? 3. X value becomes what? 3. So R2 by R1 we have taken in this case. R2 is what? K into 3A whole square into 3B whole power 1. Divided by R1 value how much here? K into A square B power 1. Okay, then 9x will be equal to 9 into 3. So x value will be equal to 3. Okay. Next one, check it here. Observe the following reaction. A plus 3B, A gas plus 3B gas gives rise to 2C gas. The rate of this reaction is given what now? Minus dA by dt is 3 into 10 power minus 3 mole late inverse. It is rate of reaction given here. Okay. The rate of reaction is given, which is equal to what now here? Rate of disappearance of A. Rate of disappearance of A. Minus indicates what? Disappearance. So rate of disappearance of A and rate of reaction given what? 3 into 10 power minus 3 mole liter inverse minute inverse, right? And the value of rate of disappearance of B, the value of rate of disappearance of B in mole liter inverse minute inverse is given what now? Y into 10 power minus 3. So from balanced equation, we can see how many moles of B? 3 moles. How many moles of A? 1 mole. Okay. So now here this rate of disappearance of A by 1 is equal to, this is what now? Rate of disappearance of B by 3 we have taken. Rate of disappearance of A divided by 1 is equal to rate of disappearance of B divided by how many moles? 3 moles. Now if we equate these two, now this value they asked here. This rate of disappearance of B they asked. Now rate of disappearance of B is equal to, this 3 will be taken this side now. So 3 into rate of disappearance of A. This 3 will go that side. So 3 into rate of disappearance of A. How much is given this one? So 3 into rate of disappearance of A. 3 into 3, how much here? 9. So 9 into 10 power minus 3. So this is what now here 9. 9 into 10 power minus 3. Is that clear, ma? So x, y value they ask here. Y is what now? 9. 9 into 10 power minus 3. Next, the rate constant, that is K. Rate constant, the activation energy, and pre-exponential factor. Pre-exponential factor is given by A. Pre-exponential factor is given by what, ma? A. So pre-exponential factor, K, rate constant, and activation energy, EA. So it is what now? K. This value is what? K. And it is what? Activation energy, this value. It is rate constant. It is activation energy. And what is this here? A. A is what? Pre-exponential factor. The value of the rate constant as temperature becomes infinite, as temperature is becoming infinite, is given here. The rate constant is given 5 into 10 power 14. Okay. So now this way we have to understand what now here. Initial rate constant is given, final rate constant is given. Okay. Final rate constant we have to get actually here. Y into 10 power 14. So K2 we have to get. K2 value we have to get. And K1 value given na? What is this K1 value here? This one. K1 value 3 into 10 power minus 4 given. K1 is given, K2 we have to get. And what is T2 here? T2 infinity value. And what is this 298 Kelvin? T1. So T1 temperature is mentioned, T2 is given infinity, and K1 is given. K1 is given how much? 3 into 10 power minus 4, and K2 is asked to calculate. Right now. So now we have to calculate first what now? This rate constant at infinite temperature. Means what now here? K2 value we have to get. Now tell me formula. Log K2 by K1 to base 10. Log K2 by K1 to base 10 is equal to what now? EA, activation energy, by 2.303 into R. Okay, into 1 by T1 minus 1 by T2. Here 1 by T2 means 1 by infinity na? 1 by infinity how much? 0. Okay, so 1 by T how much here? 1 by 298. So this value we have to calculate. Okay, so this value we have to calculate. Then we can take what now? K2 by K1 value. So this total value on substitution we'll get this total value 18.3, suppose 18.3. This total value how much we'll get? 18.3. Is that clear, ma? So here what is the unit given here? Kilojoules given, na? Activation energy is given kilojoules. Then this R value should be taken in kilojoules. 8.314 into 10 power minus 3 kilojoules you take. As we have taken activation energy in kilojoules, R also should be in kilojoules. Otherwise, you convert this kilojoules into joules. Then you can take R value in joules. Okay. Now, here in this case, if we calculate this value, what we get? 18.3. Now, K2 by K1 is equal to what? Antilog of 18.3. Okay. I'm erasing this one. Take screenshot now. Take screenshot. I will erase it. Now, tell me now what we got. Log K2 by K1. Log K2 by K1 is equal to 18.3 we got now. Therefore, antilog means what? Only K2 by K2 we take. K2 by K1. Only K2 by K1, what? Tell me now here. Yeah. Now tell me K2 by K1 is equal to antilog of 18.3. That equals to antilog of 0.3 how much more? 2. Because the log 2 is equal to 0.3 na? Log 2 is 0.3. Antilog of 0.3 how much? Antilog of 0.3 2. So 2 into 10 power 18. Before the decimal, what is the value? 18. So 2 into 10 power 18 is what now here? K2 by K1. K2 by K1. Now K2 value how much? We have to calculate. K2 value is what now? Y into 10 power 14. Y into 10 power 14. K2 by K1 value how much? 3 into 10 power minus 4. 3 into 10 power minus 4. So this Y value we have to get. This Y value we have to get. The Y value will be what? 6. Okay. So this way we have to calculate what now? So if you take this one, that side, what happens here? 3 into 2, 6, huh? 3 into 2, 6. Here 10 power minus 4 into 10 power minus 18, 10 power 14. So Y value how much we got here? 6. Okay. Next, for a given reaction, the energy of activation means EA. For forward reaction means EAF. So EAF is given what now here? 80 kilojoules per mole EAF. And delta H of reaction. Delta H of reaction is given what? Minus 40 kilojoules for the reaction. A catalyst lowers activation energy of forward reaction to how much? 10 power, means 20 kilojoules per mole. The catalyst will lower activation energy for forward reaction and backward reaction to the same extent. That point we know. Initially, how much activation energy for forward reaction? 80. And finally, how much is activation energy forward reaction in the presence of catalyst? 20. Means how much is lowered here? 80 minus 20, how much? 60. 60 kilojoules energy of activation for forward reaction is lowered in the presence of what catalyst. Whenever activation energy for forward reaction is lowered by 60, activation energy for backward reaction also must be lowered by 60. The lowering of activation energy of forward reaction must be equal to the lowering in activation energy for backward reaction in the presence of catalyst. So catalyst will increase the rate of forward reaction and backward reaction to the same extent, right? Like that we have to understand. So it's about what now here? The decrease in activation energy. So in first case, tell me what is the formula for delta H of reaction? EAF minus EAB. EAF minus EAB. EAF how much here? Means delta H how much? Minus 40. EAF how much? 80. And EAB we can calculate. So this EAB value we have to calculate. So EAB value will be 120 kilojoules. 120 kilojoules. So initially EAB how much we got? 120 kilojoules we got. So this is given minus 40. EAF is given what? 80. So minus 40, 80 given already. So EAB will be what now here? 80 plus 40, 120 kilojoules initially. Okay. Now from this 120, how much should be decreased? From 120, how much value should be decreased? 60 must be decreased. Why 60? Because in case of activation energy of forward reaction, 80 became what? 20. Means lowering how much? 60. The same thing should happen for 120 kilojoules of activation energy for backward reaction also. Na? From 120, how much should be decreased? 60. Then if you reduce to 60, what I mean here? It will be decreased by 60. So now activation energy 120 initial, finally it is 60. That equals to how much now? 2. Therefore, the ratio they asked here. Find out the ratio of activation energy for reverse reaction, backward reaction, before and after. Before means initially activation energy 120. And after addition of catalyst, what we got? 60. Why it became 60? Because the lowering should be 60. So like this 120 by 60 will be equal to 2. Okay. So it is about what now? The discussion of JEE Mains Model 4 examination, which is conducted on 5th September. Right now. Bye. Good day.